Welcome to The Explainer. Today we're digging into the physics of materials. We're going to figure out why some things, like a rubber band, snap right back into shape, while other things, well, they just stay bent. Yep, we're talking all about elastic and plastic behavior. It really all boils down to this one simple question. Think about it for a second. You stretch a rubber band, you let it go, and poof, it's back to its original size. But you take a paper clip, you bend it, and it just stays that way. This little observation, it's the key to understanding how all kinds of materials handle stress. So here's our game plan for today. We'll kick things off with the basic concepts, the snap and the bend. Then we'll dive into how materials actually store energy when you stretch them. After that, we'll get our hands dirty with some real problems. And we'll wrap it all up with a quick review to make sure you're ready for any exam. Okay, let's jump right in. The very first thing we need to get our heads around are the two main ways that materials change their shape, or, deform, when you apply a force to them. First on the list is elastic deformation. This is that snapback we were talking about. When something deforms elastically, the change is only temporary. You can imagine the atoms inside are being pulled apart, but they're still connected, just waiting to get back together. So the moment you remove that force, they snap right back to their original positions. And on the flip side, you have plastic deformation. This is our bent paper clip. When a material is deformed plastically, it means you've pushed it too far. The atoms inside have actually slid past each other into new positions, and they can't find their way back home. The change is permanent. It's irreversible. So really, the most important thing to remember is this difference right here. Elastic deformation is reversible. It's temporary. The atoms go back to where they started. Plastic deformation, on the other hand, is permanent and irreversible. The atoms find a new place to settle. It's this one difference that decides everything. And this graph, it shows us that exact tipping point. See, on a force extension graph, you've got this straight line part. That's the elastic region. But then you hit a point, right here at E, called the elastic limit. If you apply a force that pushes the material past that point, that's it. You've entered the plastic region, and there's no going back. The material is permanently changed. All right, let's move on. Because when you're stretching or bending something, you're not just changing its shape. You're actually storing energy inside of it. And that stored energy has a specific name. We call it elastic potential energy. It's basically the energy an object has just because it's been stretched or compressed. Think about that rubber band again. The work you do to pull it back is stored inside it, just waiting to be released as soon as you let go. Now here's the really cool part. We can actually see and measure this stored energy. It turns out that the work you do to stretch something, which is the same as the energy stored in it, is simply the area under its force extension graph. If it's a nice simple spring, that area is just a triangle. And that picture of a triangle on the graph leads us directly to these two super useful formulas. The work done, or the energy stored, is either 1/2 times the force times the extension, or if you happen to know the spring constant, K, it's 1/2 K times the extension squared. Simple, but incredibly powerful. Okay, that's enough theory for now. The absolute best way to really get a feel for this stuff is to see it in action. So let's try to solve a few classic physics problems. So here's our first problem. We've got a spring, we know its spring constant, and we know exactly how far it's been stretched. The question is pretty straightforward. How much energy is it storing? So all we have to do is follow 3 simple steps. First, pick the right formula. Second, and this is super important, we have to convert our units. Those centimeters have to become meters. Then we just plug in the numbers. A quick tap on the calculator, and we get our answer, 4.7 times 10 to the negative 3 joules. Easy as that. All right, before we jump into another calculation, let's do a quick check on the language. You're going to see this phrase a lot, so let's make sure we've got it down. What does it actually mean to be extended elastically? To put it simply, it just means the stretch was temporary. The material was pulled, but it didn't go past its elastic limit. So as soon as you let go of the force, it snapped right back to its original shape, no questions asked. Okay, let's try another one. This time we're dealing with a wire, and we've got some different numbers. We know the force constant, and we have an extension, but this time it's in millimeters. Let's find out how much energy is stored. We're going to use the exact same formula. The only trick here, again, is the unit conversion. We have to be really careful to change those 1.4 millimeters into meters before we plug it into the equation. Once we do that, we solve it and find that the stored energy is 0.054 joules.
Now for a little twist. This one flips the whole problem around. This time we're given the energy and the force constant, and we have to work backwards to figure out the extension. So how far was this rubber band actually stretched?
To crack this one, we just need to do a tiny bits of algebra. We take our original formula and just rearrange it to solve for x, the extension. Once we have our new formula, it's back to business as usual. Just plug in the numbers. The math gives us an extension of 0.042 meters, which is, of course, 4.2 centimeters. All right, to wrap things up, let's make sure all these concepts are really locked in. We're going to do a quick rapid-fire round with a couple of typical exam questions to see how this stuff gets tested. Here we go. This is an absolute classic. This question gets right to the core of everything we've talked about today. If you can answer this one clearly, you've definitely got a handle on the fundamentals.
And like we've said, the answer really just boils down to one word: reversibility. Elastic deformation is temporary and reversible. Plastic deformation is permanent. That's the key.
Okay, here's another very common question, this one focusing on those graphs we looked at. Remember the graph? What does that space underneath the line actually represent? The area under that curve represents something called the strain energy density. Now, that sounds complicated, but it's just a fancy way of saying how much energy is stored in each little bit of the material's volume while it's being stretched. So what's the big picture here? Well, these ideas aren't just for a physics test. They are the absolute bedrock of modern engineering. They explain why a skyscraper can sway elastically in the wind and not snap, and why the crumple zone of a car is designed to deform plastically to keep you safe. So the final thought I'll leave you with is this. How many things in the world around you rely on this delicate balance between snapping back and staying bent? It's literally everywhere.